Hello, in this video, we are going to look at how we can use parametric equations to find an area under the curve. There's a lot of words in this description, but it says suppose the function y equals h of x is non-negative and continuous on the equation on the interval alpha to beta, which implies that the area bounded by the graph of h and the x-axis equals the integral of h of x dx, or the integral of y dx. If the graph of y equals h of x is traced exactly once by some parametric equations, then by substitution, this is just basically a u sub that happens, the area bounded by h is not only this integral of h of x dx, it can also be the bounds of the parametric equation from g of t f prime of t, where this is our y and this is our x derivative, if alpha equals f of a and beta equals f of b. We can also switch these. It could be if alpha equals f of b and beta equals f of a, and all that would do is switch the bounds. So we can switch with a u substitution between using an integral in terms of x versus an integral in terms of y, of t, if we have a parametric equation. So we want to take a look at this example of using the parametric equations of an ellipse centered at the origin, x equals a cosine theta, y equals b sine theta, between 0 and 2 pi. We know typically what we can do is find the integral of the function, whatever the ellipse is, and the function of the ellipse would be y dx. Now, since it's a circle, we'd have to worry about bounds. But we know, being an ellipse centered at the origin, if I can find this 1/4 of the ellipse, I have the whole thing by multiplying by 4. So I'm going to take that 1/4 and set up this equation. So we're going to have 4 of those quarters that are shaded in red. And since this is a dx integral, our bounds are going to start as being in terms of x. So that would be from 0 to a. What this formula above tells us is that this integral from 0 to a would be the same as the integral of g of t times f prime of t dt, with 4 of those, where g of t is the function for y, that's the b sine theta, and f of t is the function for x. F of t equals a cosine theta. So f prime of t is negative a sine theta d theta. We do not have the d theta on that. And so, because these are actually in thetas, we're going to switch that t to thetas everywhere, just to keep our variable the same throughout. But in general, t and theta represent the same thing. And so we actually have 4 times the integral of b sine theta times negative a sine theta d theta. Last thing we would need to do is find these new bounds. The bounds were in terms of x. So when x equaled 0, 0 equals a cosine theta. Meaning theta, the first time a cosine theta would be 0 would be at pi over 2. So that lower bound of 0 becomes a pi over 2. And when x equals a, our upper bound, a equals a cosine theta, or 1 equals cosine theta, meaning theta equals 0. So our integral is from pi over 2 to 0. Rewriting this integral, we have a negative AB with our constants that can come out, times 4, 0, pi over 2 to 0, of sine squared theta d theta. This negative can switch the bounds. We haven't seen that really since U sub section, but this is U sub. So I'm going to remove the negative and switch the bounds to have the bounds be from 0 to pi over 2. To evaluate the integral sine squared theta, we use the power reducing formula, which is that sine squared is equal to 1 minus cosine 2 theta all over 2, which I've pulled out front here, d theta. And now evaluating this, we have 2ab of theta minus 1/2 cosine, minus 1/2 sine 2 theta, evaluated from 0 to pi over 2. Plugging in bounds, we get 2ab pi over 2 minus 1/2 sine of pi minus 0 minus 1/2 sine of 0 where this is all 0, 1/2 sine of pi is 0, leaving us with pi times AB as the area of an ellipse. So if we know those two extreme points,